Hey, what's up? Today I'm gonna show you exactly how I implemented Worley Biomes into my Voxel Engine. Now, Worley Noise creates really cool shapes, perfect for biomes. Now, this method of biome generation is really hard to find videos showing you exactly how to implement. So I felt like it's my duty to share the knowledge of everything I've learned so far. Yes, I know there are Worley tutorials out there, but none of them talk about biome classification, nor do they talk about blending, fatal information if you're going to use it in a voxel engine. First I will show you how to implement Worley completely from scratch using the Rust programming language. That is what I use for my voxel engine. I also use the Bevy game engine. Then we will implement blending. We need to know, how close am I to the forest? Oh. How close am I now? Oh. What about that? Now my voxel engine generates the world terrain based upon the biome, so blending is required. Without it, my biome's terrain would leave very abrupt terrain changes. Then we will implement biome classification. Worley noise on its own only returns a floating point value, but our implementation will assign deterministic random biome variants. Finally, we're going to see how I integrated this into my voxel engine. I hope you're ready for some code, cause it's gonna get technical. Welcome to a brand new Rust project. Let's do a quick overview of this project. So we have the cargo toml file, and the only dependency I have right now is Bevy. We're gonna use the Bevy game engine to visualize our Worley world. This project will be a library that you can use in external projects, so we have a lib file, and all we include is the Worley file. In the Worley file we will implement Worley noise, wonderful. First we need a way to visualize our Worley noise. So I set up a very basic Bevy application. On startup we spawn a texture, and we can set individual pixels based upon an X and Y value. We base the red and green value upon the X and Y position. That is why it looks like this right now. But we're gonna replace this with Worley later on. I construct this raw texture data, and to render it in Bevy, we need to construct a Bevy image. And finally, we spawn a UI node that can render this image. This code is pretty self-explanatory, so let's implement some Worley noise. You might have heard of Worley noise. You have a bunch of points scattered anywhere, and the color is based upon the distance to the closest feature point. Now, Worley noise is very similar in that it is based upon the distance to the closest feature point, except Worley noise is a bit more restricted. Instead of placing the feature points randomly anywhere, in Worley we uniformly distribute these points inside of boxes, or shall I say cells. When we do this we get similar shapes that still look organic because the points are still randomly placed inside of these boxes, but the incredible advantage of Worley is that it is super easy to make it infinitely scalable. Let's see how this code works. This is all the code you need to make a basic Worley implementation. So for Worley noise we have a input X and Y position, and this function returns a distance, the distance to the closest feature point. From the example code you saw before, instead of using the X and Y position to just color the red and green value, I instead sample Worley using the X and Y position and use the distance, and this is the result. Firstly, I put the Worley function inside this Worley struct, because there are some parameters that I want to reuse and I don't want to put that in the argument every time I call Worley get. We have a zoom value. This is effectively the cell size. A value of 10 gives us 10 units per cell size. And we have a seed. Now the cell points will be randomly generated, but to make it completely random would be useless. We need deterministic randomness, and we need a seed to set that. Our first goal is to find what cell/box that the input position is closest to. By dividing the input position by the zoom value and then flooring this value, we effectively make it so, for example, if the zoom value was 100 and the X position was somewhere between 0 and 99, when we divide by 100, that will give us a value from 0 to 0.99. And by flooring the value, we will in turn get the same cell X position for when, in this case, X goes between 0 and 99. Hopefully that makes sense. We have the closest cell position, now we want to find the neighboring cell positions. Now if we used Voronoi instead, you might check the input position against the distance to every single feature point, but we can do an optimization here. Because all the feature points lies inside of these cells, we only need to check against the neighbors from our current cell to find the closest biome. So we have the current cell position, and now we need to find the neighboring cell positions. And we can do that very simply by adding an offset. I have a const array with these offsets. Now we have the neighbor's cell position, but we don't have randomized positions inside these cells. And we'll use the cell position function to generate these random offsets. I pass in the seed parameter and the neighbor cell position. And to randomly generate a feature point deterministically, we'll use the seed and the cell position in a hashing function to produce a random number. Now we need two randomized values, a random X offset and a random Y offset. Now if we use the same input to the hashing function, we will get the same value. So I modified the input seed value to ensure x and y are completely different. This hashing function returns a U64 that can be anywhere from the value 0 to the max value of a U64. And our feature points should be placed inside of these boxes, so we can't add an offset of 50 million, so we need to rescale our randomized hash value to instead go from 0 to 1. We finally return the input cell position with our offset. We now have a loop going over all neighbor feature points, and what is left is to calculate the distance from our input position to all of the feature points and find the closest point. Finally return the closest distance. The problem with returning only the distance to the closest point is, well, how do you classify these blobs into a user-defined biome type? So let's implement that. Instead of returning the distance to the closest point, we will return a user-defined template biome type. We're not gonna use this biome type inside the world struct, so to please the Rust compiler, we need to store a phantom of the template. What we need is for each feature point to be assigned a random biome. Well, just how we randomized an offset for the feature point, we can also just randomize a biome. So we're gonna call our hashing function, passing in the seed and the cell position, and this randomized value will actually be different from the cell points values. Because if you take a closer look, in the cell points function, we add to the seed value before calling the hashing function. So all the hashing calls here use different inputs. We need to take this random value and produce a biome t. The problem is, we have no idea what this biome t is. Now from the user side, we want to use an enum for a biome. This user-defined biome type, it's just a template. We don't know about the members. We need a way to convert this random value into a variant of this enum. We can do that quite easily with a trait. Let me introduce you to a trait called biome variance. The variance function will return a list of itself. Let's implement this trait on our biome type. It's easy as that. Now we can use this biome variance function. So first of all, let's add the constraint. Now we can call the variance function. Here we have a list of all the possible variants. And we'll take the variance array and we will index into it the random value. Now this would actually crash because the random value goes from 0 to the max value of U64. Now to get it from the range from 0 to, well, the max amount of variants, we can use the modulus operator. Now we have a selected biome t. It is fetched from our user implemented variants. Now previously we stored the closest distance to our cell. Let's also store what variant we picked. We can't just set biome t here. We don't know what variants exist, so I'm going to do a quick hack here and fetch first defined biome t. This value doesn't actually matter, we just need to define it because it will be overridden in this loop. So if we find a closer position, we want to set the variant. I should rename these. Let's rename it to closest biome. Bam! And what do we return? The closest biome. The parameter type biome t must be valid for the static lifetime. Consider adding explicit lifetime bounds. Man, I love Rust, it just tells me exactly what's wrong. Let's add some bounds here. Static. And now it complains in the example code. Copy and clone. And now the Worley requires a phantom, which I briefly talked about. Now our example code is broken because previously we used a floating point value, but now we instead have an unknown type because we don't specify this Worley to use our biome type. Now we know what type we're using with the Worley, and the return value from our Worley noise function, it returns a biome. Now we need to paint it somehow, so let's add some coloring. I'm going to implement a function on the biome type. It's called color. Let's actually return a tuple of the color, and we're going to match against self. If we are a forest biome, let's use green. Red 0, green, blue. If it's a desert, we want to use yellow. Max red, max green, 0 blue. Let's just do this. R, G, B. This is no longer a noise, this is a biome. Biome color. And we push red, green, blue. It compiles! Look at that! We got biomes! And the incredible thing is, if we add a new type, let's add lava, it's going to be red. Immediately, it doesn't work. Why doesn't it work? Alright, because this variance function, I didn't actually add that to be a possibility. So let's not forget that. Easy to forget. We compile, and bam! We have 3 different biomes. Incredible. Let's play around a little bit with the zoom value. Look at that. Beautiful texture. Now you might call it a day there and be happy with this Worley implementation, but I am not happy enough because in my Voxel Engine, depending on my biome type, I generate the terrain differently. If I were to use this exact implementation, when I generate my world, we would get a huge scar in the voxel terrain. So our next evolution of our Worley code is to implement blending. Instead of returning the single biome, let's return a vector of biomes. But we also want to return the distance to that biome. So I'm gonna put it in a tuple. Let's instantiate our vector. Let's comment out this selected biome thing. And instead, insert into this vector the biome we're checking at, which I called variant. Let's rename that to biome. We add the biome and we add the distance to that biome. By the end, we return these biomes, which expects a float 64 actually. That's it, that's all. Let's fix our example code. Now when we call Worley noise, we don't get a single biome, we get a list of biomes. So let's rename it to biomes and let's loop over each biome. For biome and the distance in biomes. Actually, let's make a consuming iterator. Uncomment that for now. We can get the biomes color like so. But now we want to sum up the maybe 80% of the desert biome or 20% of the lava biome. So we need to sum it up. Total R, total red, total green, total blue. 0, 0, 0. Mutable. This red value to the total red value. If we take our biome's red value and multiply it by the distance, the closer you are to the center of a biome, the distance will be 0. So we are actually working in the inverse, but let's see what happens if we do the inverse. We do it for the red value, green value, and blue value. We can't multiply an 8-bit integer with a 64-bit floating point, so let's actually convert the total R to, instead of using an integer, use a floating point value. And then I will convert the color to a floating point value instead. There we go. After this we have totaled up how much of the forest should we use, how much of the desert and how much of the lava, but as I said, using the distance is a bit weird, but we're gonna see what happens. Then we will push the red, green, blue value, but it's a floating point value, turn it into an 8-bit value. Which doesn't work, because we don't have those variables. Total R. It's totally yellow. That's interesting. Using the distance to multiply with the color is clearly a very bad idea. If we look here in our colors, all of the colors are either red or green. I don't have any blue value. If we are far away from lava, distance will be really high. So the red and green values will be probably maxed out. As I suspected, we get really high red and green values. I was hoping we could see something cool by doing it the wrong way, but we're gonna have to do it the proper way. So we clearly cannot use the distance. Instead, we want to reverse the distance. The closer we are to a point, the closer to 0 we are, the more we want to use of that biome. First of all, let's rename this from distance to %. So, back to our Worley function. Here we return the distance, and we don't wanna do that. Actually, let me clean this up. We need to reverse the distance. The closer to 0, the higher we want it to be. Now allow me to introduce a new member here. Sharpness. I'm gonna go over it soon. To get the higher value, the closer to 0 we are, we can take the value 1 and divide that by the distance. As you can see in these examples, the closer to 0 the distance is, the higher the value. And you'll notice here we can't divide by 0, that would give us infinity, which is a number we can't work with. So if we are spot on inside the feature point, we want to fully use that biome. So to avoid this invalid number, we need to make an if check. If the number is lower than this very low floating point value, aka 0, we return a high value. Now, the sharpness value will be used to control how much blending occurs. The higher the sharpness value, the less blending occurs. By increasing the distance value by the power of the sharpness, suppose sharpness is 10. Well, in this case, as you will notice, if we are incredibly close to a biome, we will get a huge value. And very quickly as you move away from the biome's feature point, you get a much lower value. Of course, the higher the value, the more we want to use that biome. If we get a weight for the forest to be 10, desert to be 10, and lava to be 0, we should expect to use 50% of the forest and 50% of the desert. To get the percent, we simply need to take the part and divide it by the sum. So we need the sum value of all the weights, and we need to do that outside of this loop. Now that we have the sum weights, we can iterate all the weights and convert it to a percentage instead. Now, if we go to our example code, it doesn't compile because I forgot to add the sharpness variable. This is sharpness 10, sharpness 5, sharpness 3, and as you can see, it becomes more and more blurry. Congratulations, that is blending. But there's some small things we should address. If you think about it, this function always returns 9 biomes, every single cell. Biomes that are so far away that they get a percent of 0, we probably shouldn't return that information. I mean, it's pointless. And in fact, it could be a performance concern. So instead of returning every single neighbor, we're going to return a set amount. So we're going to introduce a new variable called k. If k is 1, that means we return 1 biome. If k is 2, we return 2 biomes. Instead of doing the weight calculation here, because not all biomes will be accounted for in the sum weight, we're going to move this out. Let me uncomment that. And instead of adding the weight, we're going to add the distance. Our goal now is to reduce the amount of biomes we are checking against to the k value. We can find the k closest distances by sorting the vector. And I use this function, select nth unstable by. That's a worthy function name, because I don't need the whole array sorted, I only need the top k elements, or in our case, I only need the lowest distances. This is slightly faster than a regular sort. After this sorting, let's remove from k up to how many biomes there are. Bam, it works. I use a k value of 1. If we use a k value of 2, we get the 2 closest biomes. Now, the higher the k value, the more accurate the blending will be. As you can see here, there's some artifacts right here. If we increase the k value, the more accurate it is. But the k value will impact performance. If you watched my first video on biomes, I showcased how I got artifacts in my Voxel Engine, and that is because I used a k value of 2. I haven't done a deep dive in the performance of my world generation yet, but I suspect I can increase this k value and these artifacts would be improved upon. Let's look on one final performance optimization you could do. If you call this function millions of times, which you will do if you use a Voxel engine, you might notice that we allocate heap memory every single call we do. We could reduce that greatly by moving it to the stack. In the final version of my Worley code, I utilize a library called TinyVec. Now, TinyVec is a really cool Rust library where you use it just like a regular vector, except internally it is either stored on the heap, like a regular vector, or if you can fit it on the stack, it is put on the stack. So just swapping out the data type can be very beneficial. Now, you might also notice the shapes of these biomes are very blobby. But if we go over to my real 3D example here, which I will not cover in this video, but it's essentially the same thing. Here you have the texture, just like I show you, but I also have a 3D representation. That's cool. Anyway, I can live tweak the values right here. So let's set the zoom to, I don't know, 30. Oh, by the way, I can also move around here. You'll notice my biome's shape are a bit more interesting. And that is because I actually do some offsetting of my positions. If I disable that, you will see it looks just like yours right now. But you can use noise functions to make the shape of the biomes a bit more interesting. Inside my actual real worldy code, You can see it's a bit more developed. Instead of always using Euclidean distance, I could use another distance functions. But I'm not gonna cover that. That's just a cool thing you can do. Here I added this warp settings, and my warp settings have a strength value and a noise value. And using these warp settings, I can give an input X and Z position, and I return a new position where I simply offset by a random noise strength. In my Worley calculation, which I call get over here, the only thing I'm doing differently is that I'm warping the X and Z position with this noise before I do any calculation. And that gives us really cool biome shapes. Another cool thing I implemented for my Worley implementation has to do with biome classification. Currently, the biomes are completely random, but maybe you want some specific biomes to be more rare. You want the chance of them appearing in the world to be less. Also, maybe for tooling, you don't want to include every single biome variant. For that reason, I implemented another template called Picker. The biome picker trait is very simple. It takes the seed and the cell position, and it outputs a biome. My library comes with 3 versions: any of, and weighted. The any picker simply picks any variant of the biome enum. This is the same biome classification I showed you. The any of variant lets you specify what variants that you want to generate. This could be useful for tooling. Maybe you only want to generate deserts and lava biomes. You can quickly specify that. And the weighted variant, we can classify biomes based upon rarity. That's my implementation so far. Let's take a look on the actual Voxel engine and see how I implemented this. This is the code in my Voxel engine where I construct the voxel data. There's a lot of stuff going on, but we're just gonna look on the important parts. I'm simply fetching all the chunk positions that I want to load. The most important part is here. Here is where I instantiate my voxel data. And inside this loop, my chunk generation code happens. Because biomes only exist on the X and Z plane, I traverse my voxels by finding X and Z first. Given the voxel's X and Z world position, I sample my Worley noise. Port's Worley noise returns a list of the closest biomes. Then I loop on my voxel's Y position. And it's time to generate the shape of the world. Now, different biomes generate different world shapes. So I iterate all of the closest biomes, we get the biome and we get the weight. And based upon the biome type, I simply call a different world shaping method. These world shaping functions returns a density and a top height. And I simply blend the density and top height with the weight of the biome. Finally, we have a total density and total top height, and I can set the voxel to be solid or not. Now, the actual mechanics of how I traverse to the shaping functions is a bit complex because I have hot reloadable Rust code, but the core concept of implementing this into a Voxel engine is very simple. We get a biome variant and we get a weight, how much we want to use that biome. And that's how it works!